Chaitanya, are you ready? Shayantani, can we start?
I think Chaitanya is the host for the.
Yeah, okay.
Amrita, are you ready? Hello, Amrita.
Hello?
Yes. Are you ready?
Yes.
Okay, so let's begin.
Yeah, please begin.
Good evening, everyone. On behalf of Curry Leaf, I welcome you all on the second day of Curry Leaf Days 2021. I would like to thank MTTS Trust for sponsoring this event. Curry Leaf, the math club of MTTS alumni, is organizing 5 invited talks as a part of Curry Leaf Days 2021. In today's session, we are having 3 invited talks on various topics in mathematics. Myself, Amrita K.S., and I am pursuing MSc Mathematics at IIT Palakkad. And I will be hosting this event together with Chaitanya Sheth.
Hi, I am Chaitanya Sheth. I am a TY-BSc student at the MS University of Baroda, Vadodara.
We will be taking group photographs at the end of each talk, and participants, please be ready for that. Our first speaker for Curry Leaf Days 2021 is Professor Mrinmoy Datta. He is an assistant professor at IIT Hyderabad. Professor Datta completed his bachelor's degree from St. Xavier's College, Kolkata, and he did master's degree from ISI Bangalore, and he pursued his PhD from IIT Bombay. He was a postdoctoral fellow at Technical University of Denmark and then a postdoctoral researcher at UIT, the Arctic University of Norway. His topics of interest are algebraic geometry and their applications to error correcting codes. Today, he is going to talk about mathematical aspects of coding theory. Welcome, sir, and over to you, sir.
Okay, thank you, Amrita and Chaitanya. Thanks for the nice introduction. So it is a pleasure to be here among a group of people who, so to speak, have changed my life long back when I attended a MTTS program in IIT Guwahati. That was probably in 2007. And now I get an opportunity to talk to all of you, the alumni and also the professors, hopefully, who left a long-lasting impression in my life mathematically. So thank you for inviting me to join this meeting and also to give a talk. So today I'm going to talk about mathematical aspects of coding theory. So the main application, as you can see, the words coding theory. So it is used in information theory in the following sense. So whenever some data is transmitted through a channel, so it is likely that there are some noises in the channel, and that would cause some errors in the transmitted message of the transmitted data. Now, the motivation of having this theory of priority is to detect the errors that are caused because of these noises, and also, if possible, not only detecting them but also correcting them. So one way of achieving this is to add some redundant digits to our information or the message that we are transmitting, and hoping to get the original message back using that redundant information. So here is an example that we almost see in a day-to-day basis. This is called an ISBN. So what is an ISBN? So there are 2 types of ISBN. So one is called ISBN 10 and another is called ISBN 13. So ISBN 13 is the most current model that is being used today. and ISBN 10 is still in use, but not as much as ISBN 13. But if you go to some book selling websites, for example, Book Depository or even Amazon, I think they will have both the ISBN numbers. So if you ever try to understand the meaning of the codes that are given at the end of the book, at the last page of the book, here is how things stand. So I'm going to talk about ISBN 10 and not ISBN 13 because ISBN 10 is closer to what we are going to talk about today. So let us stick to ISBN 10. So it consists of 10 digits. So let's say A1, A2, A3 up till A10. So now A1, A2, A9, they could take values from 0 to 9, whereas A10 can take value, let's say 10 also, but to keep the string a 10-digit number, it is often written as X. So, so how are ISBN codes made? So the first 9 digits, A1 till A9, they consists of some information about the book, where it is printed, where it is written, etc., where it is published. And the last digit is a check digit. So how was this A10 determined? So A10 is the unique integer between 0 and 10 that satisfies the following property. A1 plus 2A2 plus 3A3 plus 4A4 plus etc. 5A5 plus 9AN should be congruent to A10 modulo A11. Equivalently, if you would just put this A10 on the left hand side in the first equation, you will get an equation like A1 till 9 A9 minus A10, and minus A10 when we compute modulo 11 is same as so minus A10 is same as 10 A10. So equivalently, A10 has to be chosen between 0 and 10 in a way so that the equation that I have just mentioned is satisfied. It is seen that ISBN can detect a single error or a transposition error. So what is a transposition error? So if your code is A1 till A9, the first 9 digit, and suppose you have actually transposed 2 elements, suppose you have written A5 instead of A3 and A3 instead of A5, then it can detect that. However, there could be many other errors that this ISBN code is not capable of detecting. But if there is a single error or a transposition error, it can detect that error. But we must admit that this ISBN code has no possibility of detecting, or even if it detects an error, there is no possibility that it could correct an error. But it is not as such needed. After all, if you were a librarian, if you were entering some information about a book in your system, and your computer complains that you might not have correctly entered the ISBN, the correct ISBN. So then you could just read those 9 digits and then correct it as such. So here is another code that we use in our day-to-day life. This is called repetition code. So how many times it has been seen that when you wanted to say something to your friend, he or she did not understand the message, then you repeated the message 3 times, and somehow you got to agree that what is the correct message. So suppose that I want to send a binary message, so which is most often a computer would send to another computer. And suppose our message consists of 4 digits. Let's say our message is given by 1011. So instead of sending this message 1011, let me send the message 3 times, 1011, 1011, and 1011. Now I have given 2 spaces between this block, so to speak. So now the thing is, if you have received this message from me, 1011, 1011, 1011, and if there is one error, then the error could be uniquely contained in exactly one of these blocks. So then you could actually detect it. And so the error is contained uniquely in one of these blocks, and then the other 2 blocks remain unchanged. So this is kind of a maximal likelihood way of seeing it, and you would like to see how many blocks there are consistent, so then you will choose them. But then you see that this is a very time consuming procedure. If you wanted to correct 2 errors, then you have to send your message 5 times. If you had to correct t errors, you had to submit you had to repeat the message 2t plus 1 times. So what happens if you want to correct t errors? So suppose that when you have transmitted this message, t errors have occurred, then the t errors would be contained in at most t blocks, and then at least t plus 1 blocks will be unaffected by the noise, and you could just see which is the correct message. Even though this is time consuming and hence probably not so cost effective as well, it can detect errors, and if it detects error, then it can also be corrected. The errors can be corrected as well. So now with these 2 examples, let us now formally define what is a linear code. So now let FQ be a field which has Q elements. So what are examples of finite fields? So very basic examples of finite fields are Z mod PZ. You should know that there are various other finite fields, but let me not go into the study of finite fields today. And instead, I would like to conceive that after this talk, you will be intrigued to see some notions and properties of finite fields by yourselves. So, so suppose that FQ be a finite field with Q elements. If you know what are the possibilities of Q, it is very good. Otherwise, I can just tell you that this Q is always a power of a prime number. But other than the Z mod PZ, none of them are of this form, Z mod QZ. So an NKQ linear error correcting code is a k-dimensional linear subspace of the vector space FQ to the power n. So you have a field FQ, and you consider the Euclidean space, so to speak, which is n times product of FQ, and you just take a k-dimensional subspace of FQ to the power n. Needless to say, k is always less than or equal to n, otherwise you are not going to actually find an NK linear error correcting code. And this n is called the length of this code, k is called the dimension of this code. And the elements of the code C are called code words. So now suppose that NK C is an NKQ code. So then there would be k vectors which will span this NKQ code. So k vectors or k code words, whatever you want to call them. So suppose we have k code words that will generate this code. And we could actually write a k by n matrix G, whose entries are of course in FQ, and the rows are the code words that generate this code C. So this matrix is called the generating matrix. You know from your knowledge in linear algebra that such a matrix need not be unique, and they could be actually so you could actually take 2 generating matrix which will differ by taking a product with a k by k invertible matrix. So now suppose that there are 2 elements, 2 vectors or code words in FQ to the power n. After FQ to the power n is also a code. So let us call the vectors code words from now on. So suppose I take 2 code words. First one is given by n coordinates x1, x2, xn. Let me call it x. The second one y1, y2, yn. We call it y. And we have to somehow define a distance between them. Now, what could be more organic than to define the distance as follows? So, given 2 code words, for our purpose, what only thing we are interested in is the following. So, how many coordinates do the code words differ from each other? So, we define that as their Hamming distance. We denote this Hamming distance by d suffix h of x comma y. So, this is of course a function of x and y, where x and y are 2 points, and it is defined to be the number of coordinates I from 1 to n, where xi is not equal to yi. Now, if you have read about metric spaces, so you could somewhat easily check that this Hamming distance is actually a metric on FQ to the power n. And one of the important takeaways, or of course, one of the important axioms that you have to check for this is that this metric satisfies the triangle inequality. But I believe that you will check it for yourself if you are interested. So another notion that we are going to define for our purpose, specifically for linear error correcting codes, is a notion of Hamming weight of a code word. So if x is an element of fq to the power n, so this is a typo. The Hamming weight of x is given by the number of places, the number of coordinates where x differs from 0. So number of I such that xi is not equal to 0. So we are basically counting or we are basically trying to measure what is the distance of the point x with the origin. So there are some more important definitions, but there are not so many that I'm going to talk about today. This is something called the minimum distance of a code C. So this is invariant of any code words. This is just dependent on the code itself, C. We denote it by E of C. So what we do, so we take all pairs of code words X and Y, which are distinct, and we compute their Hamming distance. What we do is that we take the minimum of all the numbers that we have thus obtained, and that is called the minimum distance of C. And now we have also defined Hamming weight, so there should be something called minimum weight of C as well. We simply define the minimum weight of C to be the minimum of Hamming weight of all the non-zero code words that are contained in C. Now, using the property of C being a linear subspace of FQ to the power n, one could show easily that the minimum distance and the minimum weight of a code are actually the same. And if we have a code C, which is an NK code, namely it has length n, dimension k, and minimum distance d, then it is called an NKDQ code. So we have just recorded this information, minimum distance, in this information in the definition. So please feel free to stop me in between if you have questions. So now let us try to understand how messages are encoded and where the error occurs and how do we rectify it. So the first thing is encoding. So how do we encode our message? So suppose that C is a linear code, and let us for the time being fix a generating matrix, which is G, and we define the encoding map. Just to keep parity, I have called it E. So it is a map from FQ to the power K to FQ to the power N. How is it defined? So you just take the row vector X, which is given by X1, X2, Xn, and you send it to X times G. So you take a row vector X, X1, X2, Xk, and you send it to X1, X2, Xk times G. So you see that this X is a row vector. So this is a 1 by K vector, and G is a K by N matrix. So the multiplication is well defined, and you are going to get a matrix so you are going to get a row vector. So that is a 1 by N matrix. So you have actually encoded a K digit message into an N digit message by multiplying the message on the right hand side by the generating matrix that we have fixed to begin with. Now G has rank K, and that would ensure that this map that you have taken is a 1-1-1. Fair enough. So now what do we do? So now the following diagram that I have drawn here actually gives us a way of understanding how messages are encoded, sent, and then how do we retrieve it if it is at all possible. So first we start with an n digit, a k digit message, which is of course an element of fq to the power k. We encode it by the map that I have just mentioned above by multiplying to the right hand side by g. Then we just transmit the message. So an n digit message will go to an n digit message. So this is not really a mathematical map, but this is something that happens through a channel. There would be some noise that must be occurring here, or that might be occurring here, which may flip some of the digits, which may change some of the digits completely. But then we have to come up with a very good decoding algorithm so that I could get back the original message, which lies in this FQ to the power n, which is the encoded message. Now, since this since this encoding is a 1-1 map, if we can identify the correct encoded message here in this FQ to the power n, we could actually come up with the original message, which is a k-bit message. So this operation is called unencoding, which is a trivial thing to do. But the non-trivial part is to do this decoding. So unfortunately, it will not be possible to talk about many decoding principles, at least in this lecture, but I would try to give you examples of some good codes that are used and that are also very interesting from our mathematical point of view. Okay, so let us proceed. So now the question is, when we define a code, then we mention the length, we mention the dimension, and we also mention the minimum distance of the code in its definition itself. So why is it so that these three parameters are so important? The first thing is length. Why is length important? You can see that if the length of a code is very small, then you cannot encode large messages into this code. So we need the code to have larger length. What about the dimension? See, the dimension of the code is k, and we are trying to encode a k digit message into an n digit message. So, so you can actually think that we are trying to add extra n minus k bits or n minus k redundant digits every time we send a k digit message for our encoding purpose. But we do not want to add too many redundant digits, because what is the point? That will actually make the process time consuming and not cost effective at all. So then we want n minus k to be rather small, and also we want equivalently k to be rather large. So the n should be large, k should be large. Now here is a rough idea of how we can decode a received message which possibly have some error. So now suppose that I have our code C, which is an NKDQ code. So we show that this minimum distance actually determines the number of errors that could be detected and corrected. And the study that I am going to tell you about will show you that not only the number of errors that can be corrected and corrected is an increasing function of this D. So first, what we do is that we take a positive integer t and we take a point x in fq to the power n. We define a neighborhood or a ball of radius t. So in a usual way, so you take etx to be the set of all y in fq to the power n, such that dh x comma y is less than or equal to t. So now suppose that we have two code words c1 and c2. You can see by triangle inequality that the balls of radius, the greatest integer function of d minus 1 by 2 of c1 and the ball of radius d minus 1 by 2 of c2 will never intersect. So this follows from the triangle inequality. I have mentioned at the beginning that our distance function is actually a metric on fq to the power n. So thus, if the received message consists of at most this greatest integer function of d minus 1 by 2 errors, then the received message will lie uniquely in one of these balls around one of the points in our code. So then you know what is the point C which lies in the ball, and then you could say that what is the original message. So in particular, if there are at most d minus 1 by 2 errors that occurs during our transmission, we can actually correct them. So the moral of the story is, if we have an NKD code, we will call them a good code if n is large and also k and d are large with respect to n. So k being large with respect to n will save us time and money. And of course, if d is large with respect to n, then we can correct more and more errors. Now, one may ask that if I fix a value of n, then can we have k and d to be as large as we want? Of course, they have to be less than or equal to n, but then is it possible that both of them are equal to n minus 1, which will be the best case, I suppose? The answer is actually given by something called a singleton bound, which says the following. So if you have an NKDQ code, then k plus d minus 1 is bounded above by n. So then you cannot have k and d arbitrarily large, and one has to somehow optimize the values of k and d in order to produce good codes. But how do you do it by hand? So it is not very easy to do that, unfortunately. So how do we prove the singleton bound? This is not very difficult. So let me actually show you a proof. So C is our code with minimum distance d. So C is a code which consists of code words which is non-zero at least d of the coordinates. So I construct a space which is generated by E1, E2, ED minus 1, which are the usual basis vectors of fq to the power n. So you see that the dimension of the space that is generated by these vectors is actually equal to d minus 1, and all of the code words that you have in this code that you have just produced, which is d, will have Hamming weight less than or equal to d minus 1. So that means none of the non-zero elements of d will ever belong to C. So C and D, these are two subspaces of fq to the power n, and they intersect at only the zero vector. As a consequence, we can see that the dimension of C plus dimension of D is less than or equal to n. What is dimension of C? Which is k by definition. Dimension of D is equal to d minus 1. So k plus d minus 1 is less than or equal to n. Now, a code for which this bound is attained, that is n is equal to k plus d minus 1, is called a maximum distance separable code, or it is simply called an MDS code. One would like to ask at this point, is it possible to construct an MDS code? Of course, one idea is that if you cannot construct an MDS code, then such codes will not be given a name. So here is an example of an MDS code. This is called Reed-Solomon code, generalized Reed-Solomon code. This is, the name varies from authors to authors, but here is how they stand. So again, we assume that fq is a finite field with q elements, and R denote the polynomial ring fqx in one variable. The variable is x, and all the polynomials have coefficients in fq. If x is a positive integer, u less than q. So this is for some technical reasons, and if you want to understand it, I have to go a little deep into finite fields. That is not the purpose of this talk. So let us assume this as a black box, that I would always take u to be less than q, and I will denote by r less than or equal to u to be the vector subspace of R, which consists of all the polynomials of degree at most u. Now, what we do is that is the following. So you take a polynomial, and you could always view this polynomial as a function of fq. So given an element in fq, you can evaluate a function. So you take an element f of a small f of x in r less than or equal to u, and you take an element, let's say a from fq. You could always write down what is f of a just by replacing x by a in the expression. So keeping this in mind, we fix an ordering of q elements in fq and we call them f1, p1, p2, pq. And now we define an evaluation map from r less than or equal to u to fq to the power q, which is given by the following. So I take a function, I take a polynomial f, and I send it to the string f of p1, f of p2, f of pq. One can easily check that this map is injective, and because we have made this assumption that u is less than q, it follows that this map is an injective map. So injective map needs actually this condition u less than q, but it is very easy to check that this map is a linear map. And since we have this condition u less than q, we will see that this map is injective. So now this r less than or equal to u is a vector space, and we have a linear transformation which is denoted by e. So a vector space to a vector space, we have a linear transformation, and the image of the linear transformation will be a subspace of fq to the power q. So e of r less than or equal to u, the image of r less than or equal to u will be the subspace of fq to the power q. So it is going to be a code. It is going to be a linear code. So length of the code is going to be q. The dimension of the code, since this map is injective, will be actually the dimension of this vector space r less than or equal to q, which is of course given by u plus 1. So what is a basis of this vector space? So 1x squared up to x to the power u. So there are exactly u plus 1 elements. How do we compute the minimum distance? So first, we should know how to compute the weight of a code word. So what is a code word? A code word C is evaluation of a polynomial. So to compute the weight, we have to look at the number of coordinates where the function, where the polynomial does not vanish. So given a code C, which is eve of f for some f, to compute the Hamming weight, we need to compute what are the points or what are the number of points in fq where the function, where the polynomial does not vanish. And now you have a polynomial. So you have a non-zero polynomial of degree at most u in one variable, and you want to see at how many points it will not vanish. So it is equivalent to asking at how many points it will vanish. And we know from maybe our first year BSc mathematics that if you have a field and if you have a polynomial in one variable of degree at most d and the polynomial is non-zero, then it cannot have more than d zeros. So that means the weight of a code word is bigger than or equal to q minus u. And you can also easily produce polynomials of degree u which will have exactly u many zeros and consequently q minus 1 many non-zeros. So the minimum distance of the code is equal to q minus u. So you could now easily check that k plus d is what? K plus d is u plus 1 plus q minus u. So q plus 1, which is the length of the code plus 1. So this is an MDS code. So there are examples of other MDS codes, which are also called extensions of the Reed-Solomon codes, but let us not go into that because I have to introduce the notion of projective space if I want to do that. Okay, so here is an important notion which is often useful. This is called a parity check and the dual of a code. So on fq to the power n, we define a scalar product or a dot product, which you do usually in your vector calculus. So take two elements, c1, c2, cn, and d1, d2, dn. We define c dot d to be summation ci di. So c1, d1 plus c2, d2 plus cn, dn. And we define the dual code of C, which is denoted by C part. This consists of all the code words from fq to the power n such that C dot D is equal to 0 for all elements small c in big C. It is easily checked that C perp is a linear subspace of fq to the power n. The dimension is n minus k. It follows from rank nullity theorem, for example. And the dual of a dual code is itself not isomorphic to, but it is exactly itself. And the generating matrix for C is C part is called a parity check matrix of C. So if H is a parity check matrix, which is of course going to be an n by k times n matrix, it is going to satisfy the equation G times H transpose is equal to 0. So G was the generating matrix of our code. Let us see how it is used. So let us apply our whatever we have learned up till now to the ISBN codes that I started with. So ISBN code is a code of length 10 over F11. So what is the dimension, minimum distance, and dual of ISBN code? So you see that a 10-digit code word A1, A2, A10 is a valid ISBN code if and only if it satisfies the following conditions: A1, A2, A10. So this is a row vector times the column vector 1 to 10, that must be equal to 0. So this matrix that we have H, which is given by 1 to up to n, this is a parity check matrix for the ISBN code. So the dual of the ISBN code is generated by, is a subspace of F11 to the power 10, which is generated by this vector, this row vector 1, 2, 3, 4 up till n. So what is the dimension of this ISBN code? So if the dual has dimension 1, then the original code will be of dimension 10. And now you see that the ISBN code will never contain a code word of weight 1. So if all of the coordinates except for 1 is non-zero, then you see that this product is never going to be 0. So the minimum weight has to be at least 2, and one can produce a code word of having weight 2. So for example, you take this code word 1001. So how would it stand? So 1 times 1, in the middle all the products are going to be 0 because here all the terms are 0, and then at the end you have 10. So you have 1. So you will multiply it by 10. So 1 times 10 is 10. And then you are going to add it to 1 that comes from the first coordinate. And so you have produced a code word of having weight 2. And consequently, the minimum distance of, or the minimum weight of the ISBN code is 2. So now I would like to leave it as an exercise if you have become interested in this topic to compute the length, dimension, minimum distance, and dual of our replication code. So let me now invest into some more non-trivial examples. So this is actually a generalization of Reed-Solomon codes. So this is called a Reed-Muller code. So instead of considering polynomials of one variables, why not we consider polynomials in multi-variables? So let's say m variables. So I take fq x1 x2 xn, call it r. I fix an integer u again, and again for technical reasons, I assume that u is less than q, and I denote by r less than or equal to u to be the subspace of r that consists of all the polynomials of degree at most u. So again, just like before, and of course here we introduce one more notation. This n is the cardinality of fq to the power n, so this is equal to q to the power n. So then we fix an ordering again, just like we did for the case of Reed-Solomon codes. So and then we define the evaluation map as we have done in the case of Reed-Solomon code. So you take a polynomial, you can view this as a function on fq to the power m. So if you pick a point p1, for example, you compute what is f of p1, you just write it, and then you form the string f of p1, f of p2, f of pn. Now one can show that this is an fq linear map, which is very easy to see. And again, the condition that u is less than q will imply that this map evaluation is an injective map. So how do we compute the important parameters? So for example, what is the length? Length is clearly n, so there is no doubt about it. What is dimension? So now, since this map is injective, the dimension of the code is going to be the same as the dimension of r less than or equal to u. So r less than or equal to u is the vector subspace which consists of polynomials of degree less than or equal to u. It is spanned by monomials of degree less than or equal to u. How do monomials look like? X1 to the power I1, X2 to the power I2, Xn to the power In, where the sum of all this, all the exponents that we have is less than or equal to u. So ultimately, this boils down to computing this number that we have here, this cardinality of this set. Well, I could use one more slide, but I'm really running out of time. But let me give you the final answer, which is m plus u choosing. So the code is of length n, which is q to the power m, and the dimension of the code is m plus u choosing. How do we compute the minimum distance? So this is what I really wanted to emphasize. Okay. So now how do we compute minimum distance? So you take a code word, you have to compute its weight. How do we do that? So a code word corresponds to a polynomial in n variables, let's say f. So c, if c is our code word, then it looks like f of p1, f of p2, f of pn. What is the Hamming weight? It is the number of i's where f of pi is not equal to 0, which is equivalent to saying that it is the number of points or the number of elements of fq to the power n where f of p is not equal to 0, which is again equivalent to saying that this is equal to n minus the number of points of fq to the power n where f vanishes. So now just a remark here. So if I want to compute the minimum weight, I have to compute the minimum of this quantities with c not equal to 0. So I have to compute the Hamming weight of all the code words, all the non-zero code words, and then I have to take minimum. And if I have to take minimum on the left-hand side, then on the right-hand side, in this cardinality, I have to take the maximum. So the model of the story is the following. So I have to compute, in order to compute the minimum weight of a code word, I have to compute what is the maximum number of possible zeros that a multivariable polynomial may have in fq to the power n. Now here fq to the power n saves us, because if you take, for example, a code of, so not a code, but a polynomial in two variables, let's say y minus x squared, and suppose our field was r or even q, so then you could see that it has infinitely many solutions, and then asking what is the maximum number of zeros will not make sense, because you cannot take maximum of infinite sets, or if there are quantities in the set that are actually infinite. So but here since our field is finite, fq to the power n itself is a finite set, and as a consequence every polynomial will have only finite number of zeros. So then can we compute this maximum? So if I take a polynomial which is non-zero, of course, then what is the maximum possible number of zeros that this polynomial may admit in fq to the power n? Now this answer goes back to someone called Ord, who was a Norwegian mathematician. In 1920s, he proved this theorem. So if d is less than q, then and if you take a non-zero polynomial f of degree d, then the number of zeros is bounded above by d times q to the power n minus 1. So to the hosts, how much time do I have?
You can have 5 more minutes.
Okay, thanks. So then what we do to prove it is to use a double induction on A and B, or alternatively we could use an induction on the quantity A plus B. So let us do that. Many of you might not have seen how double inductions are used. So, so let's see how can we prove this inequality using an induction on M plus D. So M plus D is equal to 1. So the only possibility is M equal to 1 and D equal to 0. The other possibility, of course, is M equal to 0 and D equal to 1, but the polynomial does not have a variable. So what kind of a polynomial is this? So we do not consider that. So we take this M equal to 1 and D equal to 0, and the assertion is trivial. So a polynomial in one variable of degree 0 is a non-zero constant polynomial which has no roots, and the right hand side is also 0. So that takes care of this case. And suppose that our assertion is true for all the smaller values of M plus D. So you take polynomials in some number of variables of some degree such that the number of variables plus degree is less than this M plus D. And suppose that our assertion is true for all such cases. Let us now take a polynomial in M variables and degree D. So this should be equal to D, not at most D. And we distinguish two cases. The first case being the following. So there exists an element A in FQ such that x1 minus A divides this polynomial completely. So I can write f of x1, x2, xn as x1 minus A times some GA times x1, x2, xn. GA denotes the quotient of this polynomial when it is divided by x1 minus A. Note that this degree is additive when we multiply, and as a consequence, this GA is a polynomial in M variables, and it is of degree D minus 1. So the number of variables plus degree is equal to M plus D minus 1, which is of course 1 less than this. So the induction hypothesis applies, and we could do the following. So how do we compute the number of zeros? So a point is 0 of this polynomial f if it is either a 0 of x1 minus a or a 0 of GA of x1, x2, xn. So we just add the number of zeros of these two polynomials, x1 minus a and GA of x1, x2, xn. Okay, so x1 minus a, how many zeros does this polynomial have? So the first coordinate has to be a, and the other coordinates can be anything. So there are q to the power m minus 1 options. On the other hand, for the next set, the induction hypothesis is applied. So we have a polynomial of degree d minus 1 in m variables. So this is less than or equal to d minus 1 times q to the power n minus 1. If we add them up, we get the quantity as desired. Next, suppose this is not the case. So maybe I'll leave this. I'll of course share the slides with the hosts, but it is not very difficult either, but I would rather leave this. But the point is, one could prove this, and one could also show that not only this is an upper bound dq to the power m minus 1, we could also produce a polynomial which has exactly d times q minus 1, d times q to the power m minus 1 many zeros in fq to the power m. So this is actually the true maximum. So the maximum number of possible zeros of a polynomial of degree d, of course the polynomial is non-zero, is equal to d times q to the power n minus 1. How do we apply this to our study of minimum weight of the Riedmuller codes? So just from where we stopped in the previous slide, so you could see that the minimum distance is n minus this maximum, and here d has to be replaced by u. So the minimum distance is q minus u times q to the power n minus 1. And as a consequence, the Riedmuller code is a code of length q to the power m, dimension m plus u choose u, and q minus u. So minimum distance is q minus u times q to the power n minus 1. So the last concluding remark is the following. So there is a more general recipe of producing codes. The way we have seen Reed-Muller codes and Reed-Solomon codes are defined. So we, instead of taking the whole spaces, we take some special subset of fq to the power n, which are called affine algebraic sets or simply affine varieties. We evaluate on them finite dimensional linear subspace of polynomials in m variables. So by a similar technique, we could produce a code. Now note that the length of the code is exactly equal to the number of points that we have on the set that we have already started with. So in general, in most current research, finding affine varieties which has many points have become a very interesting problems, which is of course interesting from its own mathematical point of view and also from the point of view of coding theory I just explained. And also after you have defined a code using such an affine algebraic set or an affine variety using the way that I have mentioned, to compute the dimension of the code or to compute the minimum distance of the code are actually problems that are studied in combinatorics, algebraic geometry, and number theory. So this is the end of the talk. I hope that you found something interesting in this talk. And thanks again for being attentive and of course giving me this opportunity to present this talk. Thank you.
Yeah. Thank you, Professor. Yeah, we now open the floor for the questions. If you have any questions, then please raise your hand. Yeah. As Kumar Gaurav, you can unmute and ask your question.
Hello, sir. Sir, how to contact you, sir? Datta, sir, how to contact you?
Well, you could find my email ID in my webpage. If you go to IIT Hyderabad Mathematics webpage, you can locate me there as one of the
Yes, sir.
faculties, and you could just go to my webpage and find my email ID.
Sir, can you reply?
Sorry?
Sir, if I Gmail you, mail you,
Yes,
can
yes,
you
please.
reply back?
Yes, yes, I will reply.
Okay, okay. Thank you.
Any other questions?
Sir, I have a question.
Yes, yes.
Yeah, can you go back to the slide where you have an if and only if condition of ISBN?
Okay. This one or the later one?
Later one. That 1, 2, 3, that to 10, that is getting multiplied dot product and equal to 0.
Yeah.
This one. So then that vector just 1 and 1 in 2 endpoints, I mean end positions.
11 is 0 modulo 11, right? So
Okay, okay, you are going modulo 11, right? Oh, sorry, yeah, I missed.
Yeah, it seems there are no more questions. So on behalf of Karilif, I thank you, Professor, and I request everyone, for whoever it is possible, please turn on your videos so that we can have a group photo.
Chaitanya, can you enable a video for participants?
Yeah, sure. Yeah, now you can turn on your videos. All ready? So 1, 2, 3, smile. Okay, thank you. Once again, Mrinmoy sir, I thank you. We now move to the next speaker. Our next speaker for the invited talks is Professor Sukumar Daniel. Professor Sukumar Daniel is an associate professor at IIT Hyderabad. He has pursued his MSc and PhD from IIT Madras. He has vast teaching experience in UG as well as PG courses. Professor Sukumar has been associated with MTTS for a long time, and currently he is a trustee of MTTS Trust. His topics of interest include functional analysis, Banach algebra, numerical linear algebra, etc. Today he will be talking about multiplicative linear maps. Over to you, Sukumar sir.
Thank you, Chaitanya. And I also thank Curry Leaf team for giving me this opportunity to speak. Let me share my screen and tell me, is it fine? So I'm going to use yeah, so are you able to see my shared screen?
Yes, it is visible.
Okay. Okay, so there was some because of a new update, there was some issue with sharing the screen in some other form. So I am trying for the first time the Zoom whiteboard. So if there is a difficulty, please bear with me. Okay, as it has been announced in the title as well as abstract, we are going to look at multiplicative linear map. Okay, so so this one is, I assume that, so what I am assuming is that possibly second or third year BSc students must have already gone through a basic vector space course or linear algebra course. So they must be knowing what is this linear maps are. Okay. So as I said, to define a linear map, we need vector spaces. Okay. So the way we understand the vector space is you have a set V and you will have an addition. That means you can add two vectors from this set. It's a non-empty set. And you also have a scalar multiplication. Where what is this scalar multiplication? If you give me a scalar and a vector, what is the scalar? This is coming from underlying field. So this satisfying number of properties. So I'm not here writing all the information about the definition of the vector space. I'm assuming that you know what is a vector space. So it's a set, non-empty set with an addition and a scalar product. Of course, we need to mention what is the underlying field. But for this talk, I'm restricting myself always to the field is complex numbers. For me, the complex numbers. Okay, the set of all complex numbers is the underlying field. And now you know how to define a linear map. Again, in this whole talk, we are not going to consider maps between different vector spaces. Always my maps starts with this set and ends at the underlying field. So these are all maps which are starting from whatever may be the set. It may be a vector space or something later, but always going to end in the underlying field. In our case, it's going to be complex numbers. Okay. So for us, for this thing, we can consider the maps are something like T, which is going from V to C. Okay. Let me also reserve that I will call this to be, say, I'll call this as phi. Okay. So phi is a map. We call this as a linear map. Of course, what it does is that it respects the operations on the vector space. So whether you take phi of A plus B or phi of A and phi of B and then add them in the codomain, they should match. And similarly, phi of a scalar multiple of a vector is same as you multiply the scalar after finding the image. So if the map which respects the vector operations, they are called linear maps. Now the next structure that we need is a ring structure to discuss about this multiplicative map. Okay. So what is this underlying ring structure? Again, you have a set, call it as R, not the set of real numbers. It is this, again, a non-empty set where you have addition. As in the case of vector space, you can add two elements from the ring. It's a non-empty set. And you not only, you can actually multiply two elements from this set. Okay. We'll see quickly a few examples. So I call this as a ring. Of course, it has to satisfy some distributive property as in the case of vector space, plus and product, whether you add them and then multiply by a number, multiply by a element of R, or individually you multiply and then add, they will all behave well. Okay, so that kind of distributive property very well is assumed. Okay, so this I call it as a ring. And now I want to call, again, consider the map phi from this R. As I said, we are always going to the underlying. For me, the maps are going to C. Here there is no field, but I always going to consider maps which are ending in the complex numbers. So I will call this as a multiplicative map. Can you guess what would be expected? Can somebody tell what would be that, if possible? There is a product of elements. Yeah.
Yeah, it should respect multiplication.
So it should respect the multiplication. Very good. So you take, I can define what is this. Okay. And I want this to be same as pi of A and pi of B. Of course, here also the multiplication, this multiplication is coming from the complex number multiplication. So I know how to multiply two complex numbers. Okay. Let me also say at this stage, I will not always write this into. If I just write it as AB, that means I'm taking two elements from the ring R and I consider the product. Okay, so this I want it to happen for all AB from there. Then this map is called multiplicative. Now our the underlying set that we are going to discuss for this rest of the discussion is that I want both of them to discuss about linearity as well as multiplicativity. So that structure generally, let me call it as, say, algebra. There are various things. So I'll denote this as a non-empty set A. Of course, you have the vector addition, and also there is an underlying field with respect to that scalar multiplication also there. And you can also take product of two elements from this set. Okay. And this I call it as an algebra. Of course, I need to have nice distributive property. Let us, I'm not listing all of them. You know how it has to be. So this is the underlying set that we are considering. And now we can ask the question. So I consider a map again from A to C. Okay, now I can ask both. I want this to be linear as well as multiplicative. Okay, so before going ahead, so what are all these maps? We'll look at few examples for each of them and then we'll ask some questions. So first, is it, there are some things we can say. Suppose if this map is both linear and multiplicative, is it clear that one can ask the question, what would be pi of 0? Pi of 0 has to be 0 because it's a linear map. And hence, one can also ask, since it is a multiplication, we can ask, is there any multiplicative identity? Okay. So if the ring has such a multiplicative identity, then you call this ring as a ring with unit. For algebra, we call it as unital algebra. So what I mean by that is that you can find out an element in A, where I'll call that as 1. With this 1, whatever A if you multiply, I will get back 1, whether I multiply this side or that side. So if I can find out such a 1, then I call this algebra as a unital algebra. Okay. So our assumption.
I think you mean A, right? 1 dot A is A.
Yeah, yes. 1 dot A, sorry. 1 dot A is A, correct. So 1 dot A is A. Okay. So this is the underlying set for us. So we are going to always assume unital algebras. And we have to ask the question that what are all the linear as well as multiplicative maps. In other words, if you call this as the vector homomorphism, and this multiplicative map, you call it as the ring homomorphism, that maps which are respecting the underlying structure, then you can call this as algebra homomorphisms. Okay. Only thing is it's going to the C, the underlying field. And is it easy for you to see that if at all such a, in the algebra, if you have a unit, were you able to see what is pi of 1? Look at this map property. If I take A and B to be 1, then you can see that pi of 1 square. Of course, 1 into 1 is also 1, and that has to be pi of 1 into pi of 1. So pi of 1 should be same as pi of 1 square, which means if you simplify, pi of 1 either has to be 0 or 1. Okay. And if pi of 1 is 0, then you can see that the whole map becomes just 0. So if I want to have a non-trivial map, then there is no option other than saying my pi of 1 has to be 1. So what is the 1 here? Here is the 1 is the unital element of this algebra. And this 1 is an element in the complex number, which is 1 plus I as 0, 0I. Okay. So we know what are our underlying set and what is the question, and one property that we have already established. If we have a multiplicative map, it should take unit element to the scalar 1. Now let's we want to list out few examples. The first example is simplest. So I call it as the complex numbers. Of course, you have the usual addition of two complex numbers, and I can multiply scalar from the complex numbers with the complex numbers. And I can also look at multiplication of two complex numbers. Okay. So the multiplication is the usual complex number multiplication. Okay. Now, the another important sets inside this examples that we are going to look at soon are what are called invertible elements. Okay. So before going ahead, so let us all explicitly write it. So what is the unital element here? This is the complex number 1, okay, which is in sense a1 plus 0 times complex number. This is a element of this complex number. This is the unital element. And I want to find out what are inverses, what are the elements which are invertible in this. So I'll use this notation. What are the invertible elements of, I'm using a general setup. So invertible elements in complex numbers. Okay. So the definition is clear. What do we mean by invertible elements? You look at those complex numbers. I say that Z is invertible if I can find out another W such that Z into W is this unit. Okay. And so is that clear that this set of all invertible elements are Can you see what are the complex numbers which I can invert?
Non-zero complex number.
Very good. So these are non-zero. Okay. Non-zero complex numbers. If you want, we can call this as C star, which is complex numbers minus singleton zero. Okay. So these are the invertible elements in this particular example. Okay. And of course, other thing that I want to also look at is the linear maps. That's I'm looking at maps which are going from this space C to the underlying field. For me is always C. And can we list off? Can we have a list of some few example of linear maps? Yes, we can do. For example, I can take phi of Z. So I can take the maps as phi of Z is just Z, and pi of, you can check that this is a linear map. In fact, more generally, you must be knowing that you can consider this to be alpha Z, where alpha is again a complex number. Okay. One can prove, in fact, these are all the linear maps, nothing more. And you could achieve this just by observing that can you find out a basis for this complex number over the field of complex numbers. So take this as a basis and write every element as a multiple of 1 and see that you could able to capture this alpha. So all the linear maps will have this particular form. So the next example that I want to look at is the example 2, which are n by n matrices. Of course, n bigger than at least 1 or bigger than or equal to 2. Okay. At least 2 by 2 matrices. If it is 1 by 1 matrix, it is essentially the previous case. Of course, the entries are complex numbers. Okay. So if you want to just follow easily, then think of 2 by 2 matrices where each entries are complex entries. Okay. And I want to ask the similar kind of question, that what is the multiplication? Is it clear that this you can have addition? So if I give you 2 by 2 matrices, you know how to add, and you know that this is also a vector space, and scalar multiple also you know how to define 2 times of a matrix or alpha times of a matrix, you know how to define it, multiplying the scalar entry wise in all the entries. And one can also define what is the multiplication. So how you define the multiplication? You give 2 matrices A and B, you have this the natural matrix multiplication. Notice both of them are n by n matrices. So you take the ith row and then the jth column, and if you multiply, then you will get the ijth entry on the product. Okay. So that is how you define the multiplication, which is your usual matrix multiplication. And now the question is that what are all, what is the unit? Does it have a unit? Okay. So this unit has, in terms of ring, there are different notions. For this particular discussion, keep unit means, I mean looking for the one. Okay. Multiplicative identity. Okay. So is it clear which is the multiplicative identity? Because of matrix multiplication, we are familiar. So here the oneness. Yeah, can somebody?
IN.
Yes, so identity matrix. So n by n identity matrix. Okay, so this is the unit. And of course, I want to know what are all the invertible elements in this case. So what are all the invertible elements of this set? Okay. And again, this is a familiar object to you, that there are various ways. You know them as, I'm collecting all the matrices for which you can find out inverse with respect to the multiplication of matrix. So given a, I want to find out a B such that AB into BA should be this identity matrix. So I collect all such A, and that's the set. And you have various description of this. one of the description that you would learn is that these matrices are called non-singular matrices and many such. But one of them you learn is one of the characterization is you want to look at the determinant of this matrix. You want this to be non-zero because the inverse is defined through 1 by determinant and finding the adjoint and looking at them. So the invertible matrices are what is called non-singular matrices are the invertible elements of this algebra. Okay. So is it clear that the first example complex numbers is an algebra, and this example is also giving another algebra where you have multiplication, and now we can ask the question, what are the linear maps? So what are the linear maps? I'm looking at again maps which are going from this n by n matrices. I'm dropping the C. These are always entries are C, and going to this complex numbers. So can some of you give an example, easy example?
Determinant of A.
Will that be linear?
Yes, it will be.
So is it so determinant of A plus determinant of B is the same as determinant of A plus determinant of B? What about identity and minus identity?
Oh no, not there.
Okay, so let me give simple possible thing. See, if you think of this as n by n entries, suppose if I consider only one entry I'm taking, say A11, can you see that this is a linear map? Something that we have done for the complex number. If you remember, this n by n matrix is a n square dimension vector space, then the basis you can consider as only one place 1 and remaining rest of the places are 0. Call it as Eij. Ith row and jth column entry is 1 and remaining place is 0. They form a nice basis. So I can define pi of anything in terms of those bases. Right now I'm calling it as just A11. More generally, of course, you can define like the way we defined for complex numbers. So all the maps will be of the form alpha ij, where alpha ij's are scalars and the entries are coming from Aij. You have to take the summation. That's an easy way to check it. Okay, so think of, you can try that any typical map will be like this. This also you can think of. Now, these are all the nice linear maps. Okay. Now, the third example. So now we know what is a unit and what is invertible elements and what are the linear maps. So the third example, what we want to look at is continuous functions defined on 0, 1. Okay. I hope you know what is this space is. It's all those functions whose domain is 0, 1 and ending up in, I'm right now, as I said, I'm considering complex valued maps such that f is continuous. So I consider all continuous maps which are going from 0, 1. And is there any natural, we all know that this is a vector space. I hope you remember how you define, take two functions and how you define the addition. Addition is defined, of course, unless you say how it behaves at each element. So it is f of x plus g of x. And alpha f also one can define. This is alpha times f of x. And now I'm asking, how do I define f multiplied by g? Okay. Yeah. So is there any easy option? There is a natural option.
of x into g of x.
Yes, so it's f of x into g of x. We were able to do this because f of x is a complex number and g of x is also a complex number. So this is a multiplication of two complex numbers. Okay. So this is the scalar multiplication, and this is how we define the multiplication. And you can check it satisfies all the. It's an algebra. Okay, you have to believe me that this is an algebra. Again, here we want to ask the questions. So what is the unit? Does it have a unit? Unital element. So what do we mean by unital element here? F into, I'm looking for h such that f into h should be f. So is it easy for you to guess?
Constant function 1.
So the unit element is the constant function. So it is the constant function. I continue to call it as just 1, but in this here it is actually 1 of x is actually constant 1. Okay. For all numbers in 0, 1. Okay. This is the constant function 1. Now one can ask as we are progressing the same questions we want to ask. So what are the invertible elements of this space? So it's now we need to ask, just go back. Unital element is 1. So I'm asking what are all the functions which are invertible. That means I'm looking for f is invertible. If I multiply f into g, I should get the constant function 1. But by definition, this is constant 1. So by definition, it is f of x into g of x is the constant function, constant 1. So I am trying to find out what is the g. So is it clear? If at all f is invertible, what should be g?
1 by f of x.
1 by correct. So if at all the g is invertible, then g of x has to be 1 by f of x. Okay. So that gives you a condition immediately that if my f of x should not vanish. Okay. So if my f does not vanish at any point of the domain, which is closed interval 0, 1, I can define this function g of x. But remember, I have to make sure that g is also in C of 0, 1. So this is something that you might have learned. If you have a function f, and if it is not at all vanishing on the closed interval 0, 1, then 1 by f is defined as well as 1 by f will be also continuous. Okay, so there is no problem in saying that this inverse is also an element in C of 0, 1. So precisely, I'm looking at, so what are all the invertible elements? Those functions such that this f of x should not vanish. That is for all x, the domain, f of x is non-zero. So all such functions, okay, they are going to be invertible elements. Now the next module that we are looking at, what are the linear maps? Okay, so this linear map is phi. It should go from the domain, which is the space algebra. So remember, it's a closed interval 0, 1. My writing is, this is the map that we are looking. So the way that we need to define, so pi of, if you give me any continuous function, I should tell what is this value. So can you, any of you, try to give a linear map on this? So given a continuous function which is going from 0, 1 to complex numbers, pi of f, I want it to be a complex number. So given a f, is there any way to find a complex number? Look at this.
You can choose the evaluation map at any point in 0 to 1.
Correct. So one way is that, so I can choose, maybe I'll evaluate at 0 or I evaluate at any point. So more generally, so specifically you can say that f of 0, this is a map, okay? But more generally, you can also say that fix x in 0, 1 and define the map phi of f as f at this point x. Okay. So so this is evaluating at the point x. So I use the notation pi suffix x. So with that notation, it's actually pi 0. So I can have pi 1, pi 1 by 2. These are the things. So these are all the linear maps. So these examples we have seen, what are the invertible maps and what are the linear maps? What is the unit element? And in the complex numbers also we have seen. Our aim is to look at, understand the multiplicative maps. So let's go ahead with that particular thing. So we want to identify what are the multiplicative maps among these linear maps. That's the next question that we want to take up. But before going ahead, some consequences. As I said, if my pi is multiplicative, which is same as saying pi of AB is same as pi of A into pi of B. This is true for all A and B coming from the underlying algebra. Okay. Now, is it clear that suppose if I have a multiplicative map, is it easy for you to see what is the value of pi of A square? It will be pi of A into pi of A. So I will write this as pi of A square. So the square, if it is outside, after finding the value, I'm squaring it. Okay. So is it clear that if the map is multiplicative, then this is true? So this implication is true. So multiplicative implies this. These maps are generally called as Jordan maps. Of course, the name is not so. If you don't remember the name, that's not an issue. So multiplicative maps are Jordan maps. So the natural question is whether Jordan maps are also multiplicative map. So first, let us understand whether this is actually true. The idea is something that you have used number of times. For example, if I give you only a norm, and if you want to find out an inner product, so I know what is, because I have, if at all it is coming from an inner product, the norm tells me I know how to find out inner product A with A. But to define inner product, I need to find out A into B. So if I have information about only A and A square, and I want to get the mixed terms, AB terms, there is an obvious strategy that we exploit all the times. Instead of using A, I will start with A plus B and then square and then use this equality to get some information. So that's what we will also do now. So since this is true for all A, in particular, it should be true for an element A plus B square also. Okay. And that is same as pi of A plus B whole square. So first, let me expand this. So this is pi of A square and A plus B into A. This is AB and then BA and then B square. On the other hand, if I find out what is pi of A plus B whole square. See, these two are equal from this assumption, whatever is given to me. So this, if I look at, since if I assume it is also a linear map. Okay. So now we are assuming phi is then I can see that this is phi of A, phi of B, this whole square. And expand this, and you see that this is, these are complex numbers. So no problem in writing in this way, pi of A. And again, now use the linearity to expand this part as pi of A square and pi of AB plus pi of BA plus pi of B square. Okay. Since it is given to me that for every a, pi of a square is same as pi of a whole square, is it clear that these two terms will be same? So these two terms also same. And it is given to me that these two things are same. So this term should be same, whatever is remaining. So I get pi of AB plus pi of BA.
Sukumar.
Sorry.
Yeah. Pi of B squared should go to pi of B whole squared.
Sorry. Yeah. So this is, yeah. So this goes to this. So these two things should be same. Which means, so these two things are equal. And is there any assumption that you want to put on the algebra that tells me the following? I can conclude this. Can somebody think of why I should write AB and then BA? Suppose if these two are equal, then it is 2 times pi of AB. Then I will cancel with 2. I will get this. And that I can assume. Yeah. Can somebody suggest what is the simple assumption that I can put?
Multiplication should be commutative.
Correct. So if my algebra is also commutative, so if my A, if this is commutative, that is AB is same as BA, then this is same as this and you will get this. Okay. So what we have done is, if I assume linearity and the underlying algebra is commutative, then we also getting this way directly. Okay. So whether you call it as a multiplicative map or a Jordan map, both of them are same. Okay. Now, so there is another, we are going to conclude about the multiplicative of map among the linear maps. So if it is linear, and whether you say multiplicative or Jordan, they are same. So the another notion that which is connecting these two things is what is known as spectrum of an element. Okay. So thus it is. So what is this? It is all those complex numbers. So this spectrum is something that is familiar to you in the case of matrix. Okay, you look at A minus lambda and find out the determinant and find it the lambdas where A minus lambda determinant is 0, and you call that as an eigenvalue. So this is just the extension of that notion. Okay, so it is lambda times 1 minus A. Okay. So this is not inverted. Okay. So let us understand this bit. So this is all those complex numbers for which what we know what is this one. This is the unit element in the underlying algebra, and lambda is a scalar, so I can multiply them minus A. That should not be invertible. So if you want to go back, let's look at this example, each of them. Suppose if I want to find out what is the spectrum of an element in C. Okay, so Z is an element of C. I want to find out what is the spectrum of, say, Z. It is all those lambda such that my lambda times 1 is here the complex number 1 only. So lambda minus Z, that should not be invertible. Okay, so what are the non-invertible elements? It's complement. It's only 0. We want that to be 0. So is it clear that this is nothing but just the Z? So the spectrum of any element in the complex number is just the same number, same complex number. And suppose if I take a matrix here, for this algebra, I take a matrix from n by n matrix, and I ask what is the spectrum of the matrix A. It's again all those complex numbers such that my lambda I lambda times identity matrix is the one I'm using. This is not here. This is not here means you can see that the determinant has to be 0. So this is, you want it to be 0. Okay, which you called it as the eigenvalues. For the third example, if I ask, so fix an element in the algebra which is C of 0, 1, and ask the question, what is the spectrum of F? Again, by definition, it is those complex numbers such that here lambda 1 is the constant function 1 minus F. Okay, this should not be innotable. And look at what are the innotable elements for which for every x, f of x is non-zero. So what is the elements which are not here? That's where the quantifiers that we emphasize comes in. At least there exists an x. So there exists an x in 0, 1. At least this is 0. At least at a point, this is 0. But what is this evaluation? Lambda times 1 of x, constant function 1x is 1, and f of x is f of x. So if you simplify, you can see that this is all those lambda in C such that there exists x in 0, 1 such that f of x equal to lambda. So can somebody identify what is this set with respect to the function f? All those complex numbers for which there exists, at least there exists a x such that f of x equal to lambda. So I'm collecting all those lambdas. Can you identify what is this?
Image.
Yes. Yeah, correct. Range or image. Okay. So this is the range of the function f. Okay. So for an element in this space, the spectrum is nothing but the range of f. I hope you know now at least what is the spectrum we mean. In the case of complex numbers, it is the same number. In the case of matrix, it's the eigenvalue. In the case of continuous function, its spectrum is nothing but the range of the map. Okay. So that's the set that we are discussing here. Okay. Now I'm a strange condition that I want to mention explicitly. That is, if I want pi of A to be in the spectrum of A. Okay. This I want it to be true for all element in A. Okay. So I'll come back to this condition, how this is coming, but I want to see if I have this information. Suppose so if my A is an invertible element in the algebra, then can you comment what will be pi of A? Suppose given this assumption, just look at a question. Suppose I'm given that A is invertible. So is it clear if A is invertible, then 0 is not in the spectrum? Is that clear? So what is the spectrum of A? It's lambda minus 1 minus A is not invertible. I'm saying that A is invertible. So 0 times 1 minus A is not invertible is not possible. So it says that if A is invertible, the spectrum of A will not contain 0. So it cannot contain 0. But given that pi of A is in this set, so pi of A cannot be 0. Okay. So is it clear that this will imply this information? If I say that pi of A is in the spectrum of A, then I can conclude if A is invertible, then the image will not be a non-zero element. This is something very straight and you might have done. If it is a nice homomorphism, then it has to take invertible elements to invertible elements. In the case of complex numbers, invertible elements are non-zero complex numbers. So if you start with an inverted element, its image also has to be not invertible. It has to be invertible. Now, of course, one can ask the question, what about the converse? Okay. So the converse, what I need to check, this is a complex number, whether this is belongs to the spectrum. Look at the definition. So all that I need to check is that phi of A, it's like lambda now, times 1 minus this A. Okay. If this is not invertible, then I will say that this is a like complex number lambda. So that lambda will be in the spectrum. Okay. That's what I'm trying to check. But using this assumption, can you see that when I can conclude this element is not invertible? Look at the implication. The other way implication tells me that. So I try to find out what is the phi of this. If it is 0, look at this implication. If it were 0, then I can conclude this A will not be invertible. That's what I want. Okay. So try to evaluate. Of course, again, I'm assuming the map is linear. So I will phi of A is just a complex number, so I can push out. Pi of 1 is the unit element in the algebra minus pi of E. And we already know that pi of 1 is 1. In the beginning, we have observed. So this is 0. So for this element, pi of that is 0. So by this assumption, you can see that this element will not be invertible. And that is same as saying this. So the other way implication is also true if you assume linearity of the map. So whether I call this assumption or pi of A belongs to spectrum of A, those two things are equivalent. Okay. Now here comes the last part. How much time I have, Chaitanya?
10 minutes, sir.
Okay. Okay. I hope I'll be able to give the outline of the idea. So what I want to make, so just let's go back. So there are two statements we made. Whether you call multiplicative or Jordan, they are same. Other statement we made, whether you say that pi of A belongs to spectrum of A, or if at all A is, whenever A is invertible, pi of A is non-zero. These two statements are also equivalent. Okay. Now I'm going to make the statement. So if you have a map phi from A to C, and I am, of course, in all these things, I have assumed if this is also a linear map, okay, if one of these conditions, okay, these two equivalent conditions, if one of this, so if I call this as a double star and one of the condition, and this is also call it as single star, any of the condition, they are equivalent, of course. So what I want to conclude is phi is satisfies one of the star condition. For the sake of easiness, I will call. So if pi of A belongs to the spectrum of A, then we can actually conclude this will imply this phi is multiplicative. So it is answering the question that among the linear maps, which of them are actually multiplicative. Okay. The condition that we want is for all A in A, if pi of A is in the spectrum of A, which is of course equivalent to the other condition we said, is same as saying pi is multiplicative. Okay. And is it so which implication is the one which we want to check? Okay. So let's say one of the implication is quite easy. Suppose if I assume phi is multiplicative, is it clear this is true? If it is multiplicative, is it clear that why pi of A has to be in the spectrum of A, or equivalently, whenever A is invertible, pi of A is non-zero? Because if it is multiplicative, it is also linear, so it is a homomorphism. So if I start with an invertible element, it should map to non-zero element. Okay, so this implication is very immediate. Now we want to look at only the other way implication. I hope I'll be able to give overall idea. There are various proofs in the literature. See, so far, if you look at, we have defined nothing about any analytic structure. It's about only algebraic structure. Okay. So to prove the other way implication that it is multiplicative, we need to show pi of a square is same as pi of a whole square. That is Jordan, is what we will try to show. But here comes the picture that the theorem is not true. The statement is not true in general as it is, but it is true unless you put some analytic condition. Okay. So the moment you see analytic condition is going to play a role, if I want to show the equality, we will try to show, even to show the equality, we will try to estimate this. So these are complex numbers. So we will try to estimate and see that it is a small number. Okay. And if we can show that this estimate is going to 0 or less than epsilon, whatever, for any positive epsilon, then we can conclude these two things are equal. So that's going to be the rest of the discussion. So aim is to estimate pi of a and pi of a square. So the way that we are going to do the estimation is to, it's not straight as such, but there are various proofs. And one of the proof which involves just your theory of equation that you have learned, that helps to get this. So I'll start with this. So fix a natural number. Of course, fix an element in the algebra also. And then define this. So I will drop this one because we know by context what is this one. So I look at the power of this and I'll evaluate this map. There's going to be just calculations and then observing the estimations. So what is this? So I will try to expand. You know how to expand this. It is lambda to the power n and then n choose 1 and then lambda to the power n minus 1 and minus a to the power 1 and goes on. Okay, so let me write few terms. So it is pi of lambda to the power n plus n choose 1 lambda to the power n minus 1 and minus a to the power n 1. Is 1 and n choose 2 lambda to the power n minus 2 minus a to the power 2 in the last terms. Okay, and n choose n minus 1 lambda to the power 1 and minus a to the power n minus 1 and minus a to the power n. Okay, remember I am assuming the linearity, so I can push the phi inside and I can write this lambda power n's are scalar, so I can push them out. Pi of 1, I know if it is already 1, so I need to assume pi of 1 is also 1. Then I can write this in terms of phi, and all I want you to observe is that this is actually a polynomial in lambda. After doing all these things, you can see this is polynomial in lambda. Maybe first two terms we need. So let me write it. So it is lambda to the power n plus n choose 1. This is n into lambda to the power n minus 1 and phi of minus a. Next term is n into n minus 1 by 2 lambda to the power n minus 2 and pi of minus a whole square and other terms. Okay. So the way that we are going to estimate, notice that, so we got pi of a and we also got pi of a square, and we are going to use them to estimate pi of a minus pi of a square. Okay. And here comes, suppose if this is a polynomial of degree n, so surely there will be roots because the underlying field is complex. I am writing z1, z2, are the roots. Okay. And of course, including the multiplicity. Okay. So multiplicity is allowed. Means repetition is allowed. So repetition allowed. So some Z1 and Z2 can be same. Now, can you tell what is the summation of roots, all the roots? This is just basic theory of equation. So if you have a polynomial of degree n, then you might have learned the sum of the roots are nothing but the coefficient of, if you remember quadratic equation, it's like ax square plus bx plus c, then the sum of roots is nothing but minus b by a, and the product of root is c by a. So here the next lambda power n minus 1 coefficient is n into this. So it is n into pi of minus a, which is minus of pi of. Okay. And we also know, if I take, in the case of quadratic, product means taken both the roots at a time. In the case of more roots, we can take product of 2 roots at a time, and then also we have an expression which is c by a. In this case, remember the constant coefficient is 1, monic polynomial. So I can take zi and zj. So it is something like z1, z2. If there are 3 roots, z1, z2, z2, z3, and z1, z3. Okay. So the better way
Sir,
to. Yeah.
it's almost time.
Oh, okay. Okay.
Okay.
Yeah, I'll be finishing in. I'll be finishing in 2 minutes.
Okay.
Yeah. So this, if you take, this is the expression that you get, n into n minus 1 by 2 into this coefficient is pi of a square. Okay. Now all that we need to do is that if I square this, then I get n square pi of a, the whole square. Okay. So you can see that already the n pi of a whole square is also coming, pi of a square is also coming. As I said, I need to estimate the difference between these two. So some connection should be there in this expression. So can you see that this is summation zi whole square in terms of the roots, that is a plus b plus c whole square formula. If you look at, can you see that? One last line, this square. This is nothing but taking each of the squares and 2 times all possible roots. Okay. And you know this expression is nothing but not n square pi of a square. And this is the square term, so I'll call it as it is. This is 2 times I multiply this expression, so it becomes n into n minus 1 times this pi of a square. Now can you see that I can take 1 n square pi of a square to the other side, so I get pi of a square minus pi of I missed something, and this is not here. This is whole square. Whole square minus pi of a square. This estimate, I take it to the other side and subtract, and you see that it is zi square divided by n square. And this is n, so we will get 1 by n pi of a square. Okay. And so now the one last comment, and with that the proof ends. If I want to estimate them, then I can use the triangle inequality to get this and also get this. I can say that this is 1 by n square times of such n terms, and this is 1 by n terms of this. So only condition that I need is, if at all zi's are coming from some root of the polynomial, then they should be bounded. Boundedness of zi's, the roots, and boundedness of this. Okay. And this is coming naturally if you have a norm on the space where it is and with respect to that, it is nice space. Okay, it's called complete norm space. Okay. So in this case of complete norm spaces, you can show that this both of them, because of the boundedness property, they will become 0. Okay, and hence, so all that I'm trying to say is that the algebraic, it looks like linearity and the multiplicativity are just algebraic notion, but one implying the other is coming from the underlying assumption of the norm space. Okay, so I'll stop at this stage, and I'll ask you to check using this information in all these examples, what are all the multiplicative map. Okay, so your pi of f should be an element of the range, and you can see that these are the only maps. I'll stop at this stage. Thank you.
Thank you, Professor Sukumar, for the excellent talk. So now I'll be taking the questions. If anybody has any question, you may raise your hand. I don't see any questions.
That's fine. Yeah. Johnson.
Okay. Somebody has a, Jansen sir has a question.
Yeah, so like in the case of C01, we didn't take all the linear maps. We didn't get all the linear maps. We only got some linear maps only.
Correct, correct.
So out of them, they are all multiplicative also. If we can verify that. That is what you mean.
Yes, 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 yes.
The Sanjul Mishra has a question. Is there any application of these maps?
See this application, the whole you can see, if you learn a little bit, you will be able to see that these maps are called letter characters. In fact, any space, any general space, in some sense is C of X. Okay, that can be actually characterized, which is developed by Gelfand and other people. So understanding the continuous functions and an appropriate space is enough to understand all these algebraic notions. So one can actually restrict yourself to continuous functions on some appropriate space. So C of X that you are learning as an example is a fantastic template. That's one. Second is, if it is non-commutative, you can also show that they are all behaving like matrix spaces. Okay. So though you are in your undergraduate, you are learning matrices and then continuous function, they are not only just a typical example. In fact, it captures the general structure. That can be proved using this information.
Okay. Saurav Dubedi has a question.
Yeah, in the last result, we have used the Jordan maps property. So it is true for only commutative algebra. So last result is only true for commutative algebra, right?
Yeah. So I will, for the time paucity of time, I did not do that. Even if without commutativity, one can deduce it. The method of deriving that is something similar to what you do in polarization identity. Okay, remember pi of AB plus BA, we got it. Correct?
Yeah.
So you can look at AB plus BA squares and AB minus BA square and expand it and subtract one from the other, and you will be able to prove that it is true for commutative also, non-commutative also. So the result is true even for non-commutative case.
Okay. I guess there are no more questions. I think we have time for another group photo now. So whoever is comfortable can switch on their video and we'll take a group photo quickly. Chaitanya, can you take the photo?
Yeah, sure.
Okay.
No, people are still opening up. Let us wait. Ready? So 3, 2, 1. Smile. One more. Okay. Thank you, everyone.
Okay. Thanks again to Dr. Sukumar for the excellent talk. We will now move to our last talk of today. The hosts for this talk are myself, Anvesha Roy, and Shantini Ghosh. So our next invited speaker is Professor Varsha Dani. She is an assistant professor at the Rochester Institute of Technology in New York. Despite being a computer scientist, she is a mathematician by heart. She has pursued her PhD in computer science from the University of Chicago. Years before that, she was a participant of the very first MDTS in 1993. Today, she'll be talking about reconstructing random geometric graphs. So over to you, ma'am. You may begin.
Okay, hello everyone. So let me just find my screen to share. Okay, so can you see that?
Yes, yes.
Okay, so today I'm going to be talking about, thank you for the nice introduction. I was indeed a participant at the very first MTTS, and it was a lot of fun and a long time ago now. But call out to Professor Kumaresan for making that happen. Thank you so much. Okay, so today I'm going to talk about reconstructing random geometric graphs, and this is joint work with Joseph Diaz, Tom Hayes, and Chris Moore. Okay.
Can I say something? The light is reflecting on you, ma'am. So that light.
Yeah, that's kind of unfortunate.
No, it's not fine.
Okay. I arranged it so that it would be fine, and then the sun came out. So, okay. So, what is a geometric graph? So, you're given some convex subset of R squared. So, think of a square, and you're given some endpoints in it. Okay, and you're also given a threshold R. And we define a geometric graph to be one whose vertices are the vertices that we just picked, and whose edges, well, there's an edge between vertex V and vertex Vi and vertex Vj if the Euclidean distance between them is less than R, less than or equal to R. Okay, and you may have heard of something called a unit disk graph. This is exactly the same thing when R equals 1. So here is a pretty picture. So we have 8 vertices here. They are you see 8 vertices. And how do you decide where there are edges? Well, say you look at this vertex, and then you take the radius R disk around it, and whichever of the other vertices are in there, you add the edges. Okay, so this is how you construct the graph. And so this is called a geometric graph with distance R. Okay, so what is, if you look at 2 vertices, right? Say V1 and V7. Well, what is the distance between them? Well, there's 2 notions of distance. One is the usual Euclidean distance because you've drawn this graph on a plane. So in this case, it looks like it might be about 2 point something. So V1 and V7. Euclidean distance is maybe about 2.6. Hopefully you agree. But then what is another notion of distance is the so-called graphical distance. The graphical distance means that you can't just go directly there. You have to go along edges of the graph. And then you look at the shortest path. Okay, so if I want to get from V1 to V7 in this graph, the shortest way to get there is through V8, and then V4, and then V6, and then V7, right? So the graphical distance is 4. Okay, so let me pause here and make sure that everybody understands these two notions of distance for geometric graph, because that's crucial. So the Euclidean distance is just the distance that you all know and love. The graphical distance is when you aren't allowed to just go as the crow flies. Instead, you have to go along these graph edges. So it's kind of like, when you're walking outside, you have to go along roads. So the distance is the shortest path. Okay, so why geometric graphs? Well, the first answer is, well, why not? We mathematicians will study just about anything, right? But another answer, for which I'm going to put my practical hat on, is this is a good working model for things like wireless networks or radio transmitter networks or things like that, where the vertices of the graph correspond to some devices, some transceiver devices, and the R corresponds to a transmission range. And then when is there an edge between two devices, between two vertices? It's when the two devices are able to communicate because they're within range. Okay, so that's one reason why geometric graphs are important. But now I'm going to take off my practical hat and go back to being a mathematician who'll study anything and say, well, why not geometric graphs? Okay, so the next question is, what is a random geometric graph? So I defined a geometric graph by saying, okay, you have some points in the plane, right? And then we use the underlying distance in the plane to define what the edges are. And now we've got a graph. Okay, so a random geometric graph is you start with some n, which is the number of points you want. And for simplicity, let's say that the convex set we're interested in is a square. And for technical reasons, because I want something called the density to be 1, I'll make it a root n by root n square. So it has area n. And what do I mean by the density is 1? Well, you'll see in just a minute. And I'm going to pick R to be between 0 and square root of 2n. Okay. And then I will sample n uniformly random points in the square. Okay. So here's a square. And I'll just choose some points at random. Okay. And then what are the edges? Well, I'll put in edges according to that threshold rule, which is that there's an edge between two of them whenever the distance is less than R. So, okay. So I'm gonna briefly stop and ask a question. Anybody see why I said R is at most square root of 2n? Show of hands. Am I going to get any interactive participation here? Okay, I'm going to treat that as a no. Well, the reason.
Hello.
Yeah. Hi.
Yeah. The R is strictly less than square root of 2n, so that we can fit the circle inside the square.
Exactly. So, well, not so much that you can fit the circle inside the square, but the point is the longest distance here is square root of 2n. So if I make R bigger than that, then basically every point will be adjacent to every other point, and that won't be very interesting, right? So that's why I want to take R that's smaller, and okay, so this is a random geometric graph. Okay, so let's get a feel for what such a thing looks like. So what about something like this? So we'll start with just what are the vertices? Can the vertices look like this? Anyone?
Yes, they can.
In principle, yes, they can. But here's the thing. If I sample n uniformly random vertices, then it is highly unlikely that I get all of them in this region and none of them in this region over here, right? Because any sampled vertex could be just about anywhere. So when I've got, okay, so for small n, it could happen that they all go to one side, but by the law of large numbers, once I've got a really large number of points in there, it's highly, highly unlikely that they would all go to one side like that. So this is not what it looks like, okay? Now another question is, okay, so when I put in n points, and I said that meant that the density was something like 1, what that was saying is, sorry, what happened? Yeah, what I was saying is that on average, there's about 1 point per square unit of area, right? So do you think the graph could look like this? Again, yes, of course it could. You know, if you toss a coin 1,000 times, it can happen that you get 1,000 heads, but these things are extremely unlikely. So again, this is not what the graph looks like. Okay, so what does it actually look like? Okay, so here's the thing. If I have some set A in here, okay, then what is the probability that the point, a uniformly randomly sampled point, is in this set? Well, it's the area of A over n, right? It's how much of the area of A represents all the points that you could pick in A, and n represents the measure of all the points you could have picked out of. So if you pick a random point in the whole square, the probability that it lies in A is area of A over n. Okay, so if I'm going to put n points, how many do I expect to go in there? Well, the actual number that goes in there is, for each point, it could go in with this probability and stay out with the probability 1 minus that. And so the number of points that go in that set follows a binomial distribution. and its mean is the area of A. In other words, on average, you expect to get area of A many vertices in here, but the actual number could be something off from that by a few standard deviations, or if you want to look at very low probability events, it could even be something off by that by more, but that doesn't happen very often. Okay, so a couple of properties. So the number, what we just said is that the number of vertices in the set A follows the binomial distribution, and an expectation that is the area of A. So if you look at a particular vertex, right, how many neighbors do you think it has? Anyone? Well, when is a point going to be a neighbor? Yes, I hear somebody. No, I thought I heard somebody turn on their mic. Okay. When is a point going to be a neighbor? Well, when it's inside this circle, right? How many points fall inside the circle? On average, pi r squared. So maybe, okay, you have the fact that the v was there in the first place, so maybe you want to say it's pi r squared minus 1, but we won't worry about that. So how many neighbors does a vertex v have? On average, it has pi r squared neighbors. And finally, one other question of interest is, do you get a connected graph? Okay, well, if you've got a square and, you know, n is very small, then maybe you don't get a connected graph because points are far away. Okay. Also, if you have large n, but r is very small, r is so small, in fact, that say r is 1, right? Then you probably don't capture much in your circle of radius 1. And so you might get some little trees here and some little trees here and a lot of isolated vertices. Okay, but it turns out that with high probability, when r is big enough, that is, it's at least square root log n over pi, then the graph is very likely to be connected. And when r is smaller than that, it's most likely not going to be connected. In fact, it's most likely going to be a bunch of isolated vertices with some little trees. Okay, so this is the case of interest. In fact, we're really going to be interested in R even much bigger than that. And let me show you a picture. So here is what a random geometric graph might look like. Okay. The number of vertices here is probably in the thousands. Okay. So any questions so far?
Yeah, you said pi r square. Don't you need to divide by n for that? Because that's the area, right?
Yeah, so the pi r squared is the area, but the point is that so dividing by n was going to be the probability that a single point got in. But once you've done that n times and n points have that much chance to get in, on average, you get that many, you get pi r squared points.
Okay, okay. Yeah, okay.
Right?
Yeah.
So, okay. So now, here's the thing. somebody sampled a graph that looked like this. And then they wrote down this adjacency matrix for the graph that looks like this. So what is an adjacency matrix? It's just a matrix. It's an n cross n matrix. And in column ij, you have a 1 if there's an edge between vertex I and vertex j, right? So here vertex 1 is adjacent to vertex 3, but not vertex 4, and yes, vertex 5, and so on, right? So somebody sampled this random graph and they wrote down its adjacency matrix, and then they took this nice picture, they've written down the adjacency matrix, and then they erased the picture. Okay, so we no longer have the coordinates, and most of the rest of the talk is about the so-called reconstruction problem, namely, can we get back the picture from just this adjacency matrix information, just information about which edge is adjacent to which other edge? Okay. Well, like all good computer science problems, this is NP hard. If you don't know what that means, think of it as code for computationally intractable. So our best hope is not to do it exactly, but to find, and by the way, this is NP hard, even if you know all the distances exactly. So our best hope is to find a good approximation. Okay. And putting back my practical hat on, well, why do we care about this? Well, it's an important problem to modeling the transmission of information in wireless networks. And by the way, if you think about it, you think about what this means. It means that if, say, you're talking about things like phone data, right? It means that phone data such as like where the phones are with, say, GPS or something. It means that even if you erase all the actual GPS data, just knowing which, sorry, phones is a bit weird because they talk to the cell towers rather than each other directly, but radio transmitters, right? Just knowing which one was able to communicate with which other one means that you can pin them down to location approximately, but fairly well. Well, what does this mean? It means that at some level, any sort of communications data that is out there about you, even if you think it's anonymized, there's a certain amount of privacy loss. Okay, so all right, doom and gloom. Yeah, so in a way, the fact that we can reconstruct these graphs is sort of a negative result for privacy, but on the other hand, it's a good way to model how information moves in these big wireless networks. And as you see, there's a long list of papers there. Lots of people have worked on it, and most recently, me and my co-authors. Okay, so taking back my practical hat off, let's go back to the question. So how do we reconstruct? All we've got is this adjacency matrix, right, of some ones and zeros. Yeah. How do we even recover R? I mean, forget about the graph. Can we even recover what the threshold is? Well, the answer is yes, that's easy, because from this adjacency matrix, you can easily compute the degree of a vertex, right? What do I mean by the degree? the degree of a vertex is the number of neighbors it has. Right. So for each of these, for each of the V, I compute how many neighbors it has. And remember, that is something that is supposed to be pi r squared on average. So if we get a whole bunch of samples that are supposed to be pi r squared on average, then from that we can recover r, right? Because that's just how statistics is done. You get a whole bunch of samples which are supposed, so then you look at the sample mean. The sample mean is supposed to be pi r squared. So you divide it by pi and take the square root, and that's your estimate for r. And the weak law of large numbers or central limit theorem or one of those lovely things tells you that when n is pretty large, and we're really interested in the asymptotics here, so when n is pretty large, that average you get is going to be pretty close to r. So yes, we can recover r. Okay. Now what about actual distances? So remember, the graphical distance is the distance going along a path of the graph. And that you can calculate pretty easily from the adjacency matrix, right? So this is the graph distance, and you can calculate from the adjacency matrix. And this here is the Euclidean distance, right? So if we want to be able to reconstruct the graph, we need to be able to get pretty good estimates on the Euclidean distance, right? But on the other hand, the graph distance, when these points are in the plane, the graph distance might not go straight there. It may go back and forth. So so we want to relate these two quantities. And well, one direction is easy, right? Clearly, the Euclidean distance is at most r times the graph distance. Why? Because each of these edges was at most r, and there are that many of them, and if they were all exactly r, and in a straight line, that would be the Euclidean distance, right? And the Euclidean distance is providing a shortcut, so this direction is easy, okay? But how do you get a bound? How do you go the other way? So suppose you have your points u and v, and we don't actually know where they are, but let's pretend that we did, right? And this is the line between them, right? Now, there's some random process that produced these points, right? So if I look at a sequence of convex lenses like this, okay, and each of these has width something of the order of r to the 1/3, and sorry, negative 1/3, and height r to the sorry. So each of these has width some epsilon, and height some h, right? Then the area is going to be something that is like epsilon h, and if we make that thing area 1 or area log n, that it's very likely to have a point in there. Okay, so each of these disks, each of these lenses has a point in it, and there we've constructed a path, right? And well, okay, I guess I didn't tell you what the radius is. So these things are arcs of radius r over 2, so that each of these distances are r. So once we've found a point in each of these lenses, it automatically gives you a path from here to here, right? And it turns out that we need to take epsilon equals r to the 1/3. And so that relates this distance, right? This distance here with the distance r, because these, okay, I'm not saying this very well, but what I'm trying to say is that because of, when n is large, because the way the distribution works, it's not that, you know, these are your u and v, and then in order to get the shortest path, you have to go some very long winding thing. It turns out that you can choose your path, you can choose your points along the shortest path pretty close to this line and take pretty long steps, so that the actual shortest path distance is not too many times more than the actual Euclidean distance. On the other hand, and this result was from one of the earlier papers, okay? But on the other hand, what's going on is, if you look at these segments of length r, if v was sort of just past the end of one of them, right? Then you're estimating, I mean, so what this tells you is that just r times the Euclidean, r times the graphical distance is a pretty good estimate of the Euclidean distance. But on the other hand, it can't be all that good, because if the v was just past this, right, you're definitely going to be off by something like r, right? Because you have to count this last interval as 1, even though it's just some small fraction, okay? So in other words, this error of r, well, first of all, this approach gives you an error of order r, but additionally, the error of order r might be fine when it's really long distances, when you're talking about points that are at this corner and that corner. But look at these two possibilities. If you want to distinguish them, here u and v are really, really close, and here u and v are not so close, but still within r. Well, if you just say the Euclidean distance is an approximation of the distance, then you're going to do pretty badly, because both of these just look like they're at distance r, where in fact they're not, right? So how can you distinguish between these two possibilities? So, so here is the sort of insight, which is that if you look at this symmetric difference between these two balls of radius r, right? So notice that over here, that's this very tiny thing. Whereas over here, it's this very big thing. Okay, well, this is just geometry. There's some formula that relates the distance between the centers to the area of this lens or to the area of the symmetric difference, right? And that's a formula that you can write down. Okay, so how does that help us? Well, the reason it helps us is that we have this property of these graphs, which is that a region of certain area must have that area worth of points in there on average, right? So what can we do? In order to estimate this distance, we simply, since n is large enough, we simply count how many other points fell in here and treat that as an estimate of the area. And then we invert this formula to get the distance. Okay. So you should be able to see that because there's a tiny difference, there's a tiny area here, this thing will collect only a few points, right? And therefore, when you apply the inverse of the formula to it, you should get only a small distance. Whereas here, there'll be lots of neighbors of, okay, sorry, I guess I didn't say, how do we know whether a point is in here or not, just based on the adjacency matrix? Well, in order to be in here, the point must be adjacent to U, but not to V. And in order to be in here, a point must be adjacent to V, but not U, right? And again, you can count how many such things are there just based on the adjacency matrix. Okay, and once you've done that, you can apply the inverse formula to it, and you can get an estimate of this distance. Okay, so that tells us that we can get estimates of short distances, and what I'm not going to go into is all the proof about why this estimate is a good one, but it turns out that you can get these estimates, and they're, for large n, they're very, very sharp. In fact, the error in them is something that's much, much, much smaller than R. It's order 1, in fact. It's okay. So now we can do short distances really well, but for long distances, we might still have this off by 1 thing going on, where you take a full step in the graph, and that corresponds to a distance of R, but maybe you really wanted just 1/100th of a step, right? So how do you deal with that? The way you deal with that is you look at hybrid distances. So you have 2 distant points, U and V, and so now you look at all possible neighbors of V, and you look at the distances of U in the long range to all of those, and you look at the distance of V from W in the short range, namely this approach, and then you say, which of those is the minimum, right? And the idea is that the minimum is unlikely to be achieved by something that goes really out of the way, like say that, right? Instead, it's very likely that the minimum will be achieved by something that stays pretty close to the line between U and V, right? And so if you minimize this D1 distance plus D2 distance, then this gives you a pretty good estimate. And the error is asymptotically much smaller than the R that we care about. Okay, so that tells us how to estimate distances. So back to reconstruction. So we can estimate distances, but you know, how do we reassemble all of this back into a square, right? So one tricky part is that this stuff here involves looking at these, looking at how many neighbors are in this ball and how many neighbors are in this ball. And if those estimates, they don't really work well if you're close to the edge and your ball around your point goes out of the square like that, right? Because it gets skewed by the fact that there are no neighbors over here. So, so the question is, how? So in other words, in order to do this hybrid distance, you at least need this point to be well inside the square, right? So here's the square. And I have a list of points and I have their distances from each other. How can I tell whether a vertex is in this nice central region or whether it's in this iffy edge region? Well, I kind of gave that away already, because what is the property of this edge region that we don't like? Well, it's that if you take a point there and you take the ball around it, then, sorry, that's a bad picture here. Part of that ball is outside the square. And that exactly tells us how this is going to work, because points inside are going to have degree about pi r squared, whereas points on the edge are going to have degree that's smaller, corresponding to how much of the circle around them did not have any neighbors. And degrees are something that you can calculate from the adjacency matrix. So just by looking at the adjacency matrix, you should be able to tell pretty well which points lie in this region and which points lie on the edge. Okay, so here is how we're going to go about reconstructing. Okay, so I'm going to start out with my axes, and I have a whole bunch of information about which gathered from the adjacency matrix about all the pairwise distances between the points. Okay, so what I can do now is, because I'm able to find these pairwise distances, and because I'm able to find which points are in the center, and the pairwise distances are pretty good estimates, it means that I can go through this list and I can pick out 3 points that I know to be, that I'm pretty sure are inside the square, not near the edge, and which are also additionally roughly related to each other as an equilateral triangle, right? So I picked these 3 points and I simply put them down. wherever I want, at the right distances, of course, right? Okay, now, once again, I have all these, so let's say that that's this point here, and this point here, and this point here, and I've just placed them on the plane. And how do I know how to place them on the plane? Because I know this distance, and I know this distance, and I know this distance. I admit that these are not exact, they're only pretty good estimates, but up to a pretty good estimate, I know these distances. And Euclidean geometry tells me that there's a unique such triangle. So I place them down. And then for each other point, right, I want to place that point down somewhere in the plane. So I say, okay, what is its distance to this? It's something. What is its distance to this? It's something. So let's say based on those two distances, I get two possibilities for this point here or here. Now, how do I decide whether the point goes here or here? Well, that's what the third landmark is for. I also have distances to this point, right? So if it's big, then I know the point went here. And if it's small, I know the point went here. So in this case, maybe it went here, right? So, and similarly, I have another point I want to place. And I know that it's distances from, I know it's distances from these three things. So maybe it gets placed there. And I have yet another point I want to place, and I know once again the distances from these three landmarks, and maybe it gets placed there, right? So the point is, because I know all pairwise distances, I can now just do a little geometry using these three landmarks that were in the center, and relative to those, I can place all the points. Okay, so because these distance estimates are really good and everything is pretty rigid in Euclidean geometry, what I should get when I've placed all my points is a square. And I do. What's the problem? This square is not really axis aligned. So is this a problem? Not really. Once I've done that, I just take it and, oh boy, this doesn't let me turn it. Okay, well, as a mathematician, I can totally turn this in my imagination, but this program doesn't want to let me turn it. Sorry. Okay, so I can move it over here and then
maybe you could align the axis.
Right. I want to take this picture and I want to turn it so that the axes are aligned, and that would then give me my reconstructed square, right? My problem is that this program here is not letting me do that to the picture. So use your imagination, yeah? Basically, I want to align this axis and this with these axes, and then that would give me a square, okay? So to summarize the algorithm again, first we compute all the graphical distances. So this is a well-known shortest paths algorithm. Then we find three landmarks that form close to equilateral triangles. And for all the other vertices, we estimate the distances to the landmarks. And then we do an isometric embedding of all of this into a square, and we realign it. And having done all that, what do we get? We get a reconstructed we have reconstructed the random geometric graph. Except that we haven't quite, because back in this picture, I made an arbitrary choice that, this corner of the square went here, but I could have just as well put this corner of the square here, or that corner of the square here, or that corner. So it should be pretty obvious that like this whole reconstruction, you can only do it up to the symmetries of the square itself, right? But up to the symmetries of the square, what we've shown is that we can reconstruct this random graph just from information about which matrix, which vertex is adjacent to which other vertices. And the kind of error we get is pretty small, right? So here is the main theorem. I guess, yeah?
I'm so sorry, but it's almost time.
Yeah, this is like the second last slide, so I'm just about done.
No problem. No problem.
So, yeah, so what have we shown? We've shown that for sufficiently large R, we can reconstruct distances and positions up to symmetry, and the error is asymptotically very small in R. And when R is even bigger, n to the 3/8, it actually turns out that the error is only about order log n. And so this picture shows what it shows is R is n to the alpha, and the error is n to the beta, right? And the previous results were in the range 0 to 3/14. Everyone just gets large error, but the previous results were getting this error of approximately R because of that last step. And what we're able to do is get a decreasing error in this whole range, and a very small error in this range. Okay, and finally, there was nothing special about the square. The same ideas extend to other convex sets or convex sets in higher dimensions, or other manifolds, as long as you have some handle on the curvature. And I will leave you with this picture of the same thing working on a sphere. And thanks.
Thank you so much, ma'am, for such an interesting lecture. The floor is open for questions. So if anyone wants to ask anything, they can raise their hand.
There is a question from YouTube in chat.
Yeah.
Okay.
So there's a question from YouTube. Manas Jana asks, by knowing which information of the original graph along with the adjacency matrix, we can surely reconstruct the original graph.
Okay, good question. So the thing about that, it's a question of what you mean by surely. So there's always going to be a certain amount of error that comes from all this randomness, right? And now, and moreover, computationally, it's even if you knew the distances exactly, it's a computationally hard problem to get sort of exact placements of everything. But so this fact that we get a good approximation rather than the exact thing, that's something you can't get around, unless P equals NP and all computation falls apart and that kind of stuff. So this is a little bit of error in a little bit of jiggle room you can't get around. But there's the question of the symmetries, right? There's also the question of there's 8 different possible graphs you could create. And that you can pretty much get around if, say, you had 3 marked points, right? If If you had 3 points where you actually knew the real coordinates, then from there, everything would just fall into place. Because then you would just choose those to be the 3 landmarks. I hope that makes sense. Okay.
Okay. Any more questions? Okay, I guess there are no more questions for the day. So I think it's time that we take a group picture, participants and everyone else who can turn their cameras on. Please turn that on and we take a group picture.
Okay, hang on, I first need to figure out how to stop sharing this. Okay, I guess you figured it out.
Okay, so be ready, everyone. I'm going to take the picture. Okay. Chaitanya, could you please take another one?
Yeah, sure. Okay, 3, 2, 1, smile.
Okay. So thank you everyone for joining today's talk. I would firstly like to thank all the speakers for the interesting talks that they delivered. I would also like to thank the host today who coordinated this session very well, and also the organizers who have been working day and night to make this event happen. I thank all the participants for joining today's event. However, our celebrations don't end today. Curlive Days will continue for 2 more days. So please join tomorrow for 2 more invited talks. Thank you so much. I request the organizers to stay back. The participants, you may leave. Thank you.
The live stream should be off.